The Alliance Hypothalamus Artificial Intelligence, CISNERIA Engineering, and GUROBI Optimization presents its services to optimize special transport systems. Hypothalamus Artificial Intelligence, CISNERIA Engineering and GUROBI Optimization have agreed on a technology alliance to jointly provide services to the special transport sectors, based on highly complex mathematical models. The technological capabilities of the three companies, in artificial intelligence and mathematical programming, make them ideal partners to face the multiple challenges that exist in advanced analytics applied to the transport sector. Due to the experience of the three companies, this alliance is particularly strong for the optimization of special transport systems such as the aviation industry, planning and operation of ports, and rail systems. The optimization-based applications for industries travel and transportation have been around for many years, due to the complexity of the business. The main services are workforce management, crew and drivers planning and scheduling, and staff rostering and scheduling; fleet management, fleet planning and dispatching, network planning, and timetabling; asset management, airport resource allocation, crane scheduling, vehicles maintenance, and warehouse resource scheduling; yield management, pricing, and dynamic packaging. These applications are general for the entire industry, regardless of the mode of transport. For example, optimized workforce management, in all cases implies staff sizing regulation, rostering, timetabling, and task assignment, monitoring and control. The benefits of operations research applications are cost takeout and operational efficiency, reduce costs of capital and cost-intensive resources and assets, capital expense avoidance or deferral, and better use of limited resources. Optimized workforce and improved customer service, increase quality of service and reactivity, more on-time deliveries and responsiveness, and improve employee effectiveness and satisfaction. Measurable ROI and improved profit, increased revenue and improved revenue mix. Improved market agility and reduced risk, respond to change quickly with improved planning. Smarter, greener planet, less carbon emissions and lower carbon footprint. Examples of applications of operations research in aviation industry are: optimized fleet management includes fleet planning, fleet scheduling, fleet tracking, and freight tracking. Optimal airplane seat layout. Each airplane has a limited space which can be allocated to first class, business class, economy seats and others. Some factors will influence the decisions regarding the optimal seat layout as follows: the ticket price for each seating category is different, the number of demand for each seating category is subject to uncertainty, and space occupied by each seat type. Airport planification. Capacity planning, ground holding, allocation and scheduling of aircraft in land waiting, and design the exit gates system. Scheduling of activities, allocation of exit gates, baggage claims, and programming landing and takeoff tracks. Optimized terminal management. Hierarchical decisions. Strategic planning, size resources, evaluate design. Tactical planning, check feasibility, and pre-assign resources. Scheduling, final schedule. Control, execute, update, reschedule, and see bottlenecks. Optimization of smart operations in ports. Mathematical programming and logistics operations in ports supports the following decisions: strategic level terminal allocation, and capacity planning. Medium-term tactical planning, berth allocation, macro yard planning, and maintenance of equipment. Short-term planning, stowage planning, key crane assignment, auto-loading, and discharge, yard micro-planning, manpower scheduling, vehicle routing, and maintenance scheduling. Operational scheduling, manpower scheduling and dispatch, vehicle dispatching, and stowage replanning. Below are several of the decisions that optimization of logistics operations can support. First, arrival and departure of services, ships, to port, terminals, docks, quays and tugboats. The objective is to reduce waiting times for ships and penalization cost in the harbor. The model produces the detailed activities timetables and show them in a smart Gantt diagram. Second, allocation of gantry and mobiles cranes to services. The objective is to optimize the loading and unloading of vessels and maximize key crane usage, The model considers sequencing of cranes, choice of cranes key, clearance constraint between consecutive cranes, sequence and no overlap constraints, crane sharing between two ships, and movement constraints for bridge and derrick cranes. Third, port assets maintenance activities. The objective is to minimize the maintenance cost. The model considers assets, key, gantry and mobile cranes, yard cranes, spreaders, and internal tractors, and maintenance and operational activities planned jointly. PHM considerations. Scheduling of maintenance tasks on a several weeks horizon, including allocation of staff and equipment, and sequencing and timing of maintenance tasks. Fourth, allocation of labor to activities in the port. The objective is to assignment of timetable of human resources, minimizing the number of employees hired and reducing the cost of payroll. The planning is carries out considering the pre-planning of port operations. Fifth, assignment of containers and vehicles to storage yards. This process is carried out in two stages. Stage 1, yard macro planning. The objective is to minimize the congestion in the yard for loading and unloading. The model considers optimization based on the clusters concept, connection with the future allocation of ships, and yard crane constraints. Stage 2, yard micro planning. The objective is to find quickly a stacking plan for a set of containers. The model decides for a container which sell across several clusters. The optimization of container storage considers cluster defined by macro planning, cells defined by micro planning, pre-assigned clusters, like used for transshipment containers, grouping containers considering destination, size, category, weight, and cranes constraints when stacking up. Sixth, movements of containers and vehicles between ships and yards. The objective is to assign the container to the crane as close as possible. Constraints of the model are handles the loading sequence between the yard and the vessel, location of containers and vehicles considering the future planned movements, constraints on cranes, clusters and on weight and stability and ships. The real-time decisions are which slot in the vessel, which cluster to pick in yard. Seventh, planning and scheduling of bulk port terminals. The objective is to minimize the terminal operating cost, considering the system environment which may include the fuel cost of ships. Managing bulk ports and ships becomes part of the industrial process, since it defines the supply of raw materials and the distribution of finished products that are related to industrial operations. Depending on the specific case, it must be coordinated. The arrivals with consumption in industrial plants, the departures with production in industrial plants, and the storage is level with the output of material. The optimization may affect the industrial process's speed and the ship speed. Below applications of operations research in railway sector are presented. The following activities have been modeled using operations research in the rail freight industry. Routing. Given the demand for rail freight transport, the set of operating policies under which routes will be assigned to trains and cargo must be established. Blocking. It specifies how blocks are constructed in each classification yard of the rail network. Blocks. They are the set of wagons that are grouped, since they share some initial portion of stations in their route, although their final destination is not the same. Classification yard. They are nodes that belong to the railway network where loading, unloading, classification of wagons, according to their destination, assembly of the same, etc. are carried out. Makeup policy. It specifies the list of possible blockages that can go on the output train. While the blocking models indicate the route to be followed by the load, and the distribution of the sorting work in the yards of the network, the routing and makeup models determine the routes and frequency of the trains, and the assignment of the blocks to the trains. In this way, the complete route and cargo allocation plan is composed of these three activities. Railway operations planning. Scheduling, timetabling. It is the generation of a schedule, which accommodates all train planning, satisfying the restrictions of the capacity of the railroad and the yard. Handling freight cars. It consists of the dynamic distribution of empty wagons in the network, so that the associated transport costs are minimized. Locomotive assignment: it is the assignment of the set of locomotives to the programmed trains, at the lowest cost, while satisfying the constraints of compactness and maintenance. The mathematical models used in railway operations planning are: projected demand for rail transport services, optimization of the blocking process, construction of timetables for trains, allocation of locomotives to trains, and assignment of crews to trains. Due to the complexity of the process of design, the operation plan is decomposed into a series of steps. Feedback loops results in an iterative process between models. Energy efficiency. Energy consumption, optimization of energy consumption in the journey between points, as a function of speed, load weight, slope, number of locomotives. Railway alignment optimization. Railways are threatened by geological hazards whose disastrous effects include severe economic losses as well as serious casualties. It is vital to properly consider such dangerous geological impacts during a railway alignment optimization process. However, geological factors are complex, especially in mountainous regions. In addition, economic factors are also crucial in the design of the railway alignment. Therefore, optimizing railway alignment can be termed a bi-objective cost-risk decision-making process. Like Herbert Simon, Hypothalamus AI believes that the computer-based mathematical modeling is the greatest invention of all times. Thank you for your attention.